Start the session now. A few people are joining. So, yeah. So, we are just going to talk about Dr. Haripriya Vemuganti. She pursued BTech in EEE and MTech in Power Electronics from our very own JNTU in 2010 and 2012 respectively. And she was awarded PhD in Power Electronics from NIT Warangal in 2019. And she has published papers in IEEE, IES, IET, Power Electronics, TNF, and IJE. So these are top journals in Power Electronics branch. Her areas of interest are multi-level inverters, reduced switch count configurations, fault-tolerant algorithms, front-end converters, high-power converters, battery charging converters, modular multi-level inverters, and voltage balancing techniques. Currently, she is working as assistant professor in the Department of Electrical Engineering in NIT Raipur. So on behalf of our IEEE Power and Energy Society chapter from the Electrical Department, we welcome you, ma'am, and please take over. The stage is all yours.
Yeah, thank you. And from myself, a warm welcome to one and all. As she introduced, thank you for the introduction. And can I start the session?
Yes, please go ahead,
Okay,
and you can start the session.
Okay. Right. So actually, in this session, I thought, like, since most of the students would be with respect to the UG and PG, like I thought that since the era is, there is a lot of demand in the era, and there is so much scope for the multi-level inverters, and you can see even at the UG level there is great research in terms of the papers and publications, and there is so much work that is carried out in the multi-level inverters. So I thought that reduced switch count multi-level inverters, which is nothing but the new generation MLI, that could be interesting topic for the session. So I have picked it out. Right. Coming to this multi-level inverters, I don't know why the slide is not changing. I'll reshare it again. Have it. Yeah. Right. The screen. Yeah, slide is changing. So coming to the power converters, actually, there are multiple applications of the power converters, but like in any of the application, the thing we mostly prefer is that high performance and cost effective. Because if any converter is being designed and if it is not cost effective and it is not producing good performance, actually we are not even interested in it. So there are various applications in which there is a demand for power electronic converters, and these are the few applications. These are the few broad applications in which we prefer a cost effective power converter.
Just
Hello?
one second. I think
Yes.
We are not able to see. We are able to. Is everybody able to see the second screen? We are still at the first.
Changing?
No, ma'am.
The slide is not changing.
No,
Now,
ma'am.
It's not changing.
still you are able to see only the first slide.
Yeah,
Yeah.
Don't know. Now, can you see it?
Yeah, we can see the second slide. Could you just change?
Now I'll try change and check it out. Now?
Yes.
Now
yes,
yes, ma'am.
Yeah, it's changing, right?
Yeah.
So there are the multiple applications. I think you are already aware of these broad areas. May not be in detail, but you might have already seen about these areas. But actually, in case of power converters, there are different types of power converters which are designed for high power, medium power, and low power applications. But we can go for the converters that are designed especially for the high power applications. These are the most popular configurations which is nothing but that basic two-level inverter, which will be designed for the high power, called as high power two-level inverters, multi-pulse inverters, multi-level inverters. Yes, the recent TELA, which is nothing but reduced switch con multi-level inverters. First, I will try to tell you what is this high power two-level inverter, how this has emerged from the conventional inverters, and what is the significance of this reduced switch count. Let's see the basic storyline that was happening in the bottom. I think the slide you can see, is this high power two-level inverters, the slide being visible? Yes. Yeah. You can see the first figure, which is nothing but a common bridge inverter, conventional bridge inverter, where DC is given and AC we are expecting it. Let's assume the voltage across the capacitor is being stiff. That is, it is already charged to the VDC and it is maintaining its potential. Let's ensure that. Let's assume that. Okay. So this particular two-level inverter, this is actually called, this inverter configuration, bridge inverter configuration, it is actually called as a two-level inverter. Okay, you have seen this bridge configuration of the inverter, which is designed with SCRs. I think you have seen this configuration, which is designed with SCRs, right? Okay, you might have seen where each device will be replaced with a thyristor. Right, those converters are called as line commutated converters. They have an issue with respect to the obtaining output voltage, because the thyristor devices, which are nothing but line commutated devices design, has got the limitation in obtaining the output voltage and operating frequency also. So what they try to do is that they replace each device of the thyristor with IGBT, and the advantage of this particular IGBT is it is a self-commutating devices. Not only IGBT, you can use MOSFET also, but they are self-commutating devices. So what is the advantage of self-commutating devices? It can turn on and turn off by itself. That means depending upon the gate pulse, it can get turn on. If you remove the gate pulse, it is going to remove the turn off. It's all about the triggering pulse control. So there are these are very much advantages in terms of the flexible control. So what they have done, they have taken the basic inverter and they replaced each device, line commutating device, with the self commutating device. It is the first generation, or else you can say the improvement in the first generation inverters. So if you see the second one, then I said it is two level. How can I say it is level? Level is always defined by the magnitude of the output voltage obtained with respect to the each leg. You can see this one in this figure. A phase has got the one leg where two switches are connected and they operate in complementary operation, and B phase has two legs, two switches, and C phase has the two switches. So the two switches connected in the A phase constitute of the one leg. Similarly, the switches connected in the B phase will be constituted the second leg, and similarly with respect to the C phase. So if you see with respect to the output voltage between A and O, you can see if the output voltage between A and O, you can see the bottom leg. If we turn on the top switch, if we turn on the top switch of the A leg, what will be the voltage of VAO? VDC? Because in a leg, both cannot be turned on. If the upper switch is turned on, then obviously the voltage between A and O terminals will be equal to that of VDC. Similarly, in case if bottom switch is turned on, making the top switch open, the output voltage will be 0. Now someone may ask, why can't we make sure that both the switches are turned on? No, we should not ensure that both are on. If both are on, what is the problem? Because it may lead to the shoot through and lead to the high amount of the current that is flowing through the complete leg. So it may lead to the damage of the over leg or over current and over voltage issues, and it will lead to shoot through. So it should be avoided. So that's the reason why they use a dead band. That means between these two triggering pulse, for example, this pulse is going to on and this pulse is going to off. Okay, the bottom pulse is going to off. In such a case, they will try to create a delay. That means they will try to turn on this complete lower switch only after the upper switch is completely turned off. So for that, it will be usually in terms of microseconds or nanoseconds. It is called as dead time. It is called as dead time. Okay, it is called as dead time. Okay, so that is so. But what is our context right now? What is the voltage between A and O? That means if the switch is S1 and if it is S1 bar or somewhere, if S1 is on, the voltage VOA or VAO, the voltage VAO is equal to VDC, obviously. Because when this is on, this will be off, the voltage VAO will be VDC. When the bottom switch is on, VAO is equal to 0. This is already known. But the point is like, that means in every leg, the upper switch will be on, the output voltage, that means voltage across this particular midpoint of the leg and the bottom point of the DC, or else you can say negative, this is called as negative trial. This is called as negative trial and this is called as positive trial. So the voltage between the midpoint of the leg and the negative trial of the DC is called as, this voltage is called as VAO. Let me call this as a terminal voltage. Let me call this voltage as terminal voltage. So this terminal voltage is varying between VDC and 0. VDC is when we on S1 and when we off S1 and we turn on S1 bar, S1 dash, obviously as they are complementary, we are getting 0. That's fine. Now, if all the legs are operating in the same way, what would be the output voltage? That means this is producing VDC and 0. It is also producing VDC and 0. It is also producing VDC and 0. It is VAO, it is VBO, it is VCO. So in that case, VAB will be equal to 0. You will not get any line voltage. Because the voltage with respect to A and B terminals, B and O terminals will be A and O terminals and B and O terminals is same. That means if you try to see the voltage difference between A and B, that means A and B will be at the same potential. So if you want to get the line voltage between A and B terminals, then what should be there? There should be a phase difference between the output obtained with respect to the A phase and the output obtained with respect to the B phase. There comes of operating where, for example, I have taken VAO, S1 is on VDC and I have ensured that the VBV voltage is 0. So in that case, what will be then VAB voltage? It is VDC minus 0, it is VDC. In next case, I pushed out, I have turned off S1, I have turned on S1 bar, and I have ensured that the voltage of VAO is 0. So VBV is also 0, I have made. So the voltage magnitude of the possibility of getting line voltage as 0. And the third magnitude, let VAO be pulled to 0 and VBO be pushed to VDC. By turning on the upper switch of VBO, we can make VBO voltage as that of VDC. So according to this, what is the output voltage? 3 level. That is, if you see, this is actually the line voltage. So it is plus VDC, it is 0, this is minus VDC, this is VAB voltage. This VAB voltage is called as a line voltage. But in this, how many magnitudes are there? VDC is one magnitude, 0 is a second magnitude, 3 is the minus VDC is the third magnitude. So this should be 3 level actually, isn't it? This should be 3 levels, number of magnitudes in the voltage corresponding to the level of that particular waveform. So in this particular waveform, if you try to see, this corresponds to 3 level. But we say it is popularly 2 level inverter. Why? Level is always defined with respect to the output obtained with respect to the one leg, only one leg. Per phase only we have to talk. Per leg or per phase we have to talk. So with respect to the per phase, there are only two possibilities of getting the magnitude, VDC and 0. So that's the reason why this is called as a 2-level inverter. But though this is going to produce a two levels in the output voltage, okay, and to obtain the desired output voltage and to make it uniform, there is a phase difference that is created between A and B legs as 120 and B and C leg as 120, again C and A as 120. So we will give a consequent phase difference and we will obtain it. Okay, I'll show you the simulation of this also. But before going for it, what is the problem associated with this particular configuration is that when you take this particular configuration, what is the device rating of the switch S1? The device rating of the switch S1 should be equal to VDC, because when the upper switch is on, the total voltage will be appeared across the lower switch. Similarly, when the lower switch is on, upper switch will be excited with an voltage of VDC. So the device rating is VDC. So when you go for the high power applications, the device rating can be equal to that means if the DC link voltage is some 3000 volts or 6000 volts or 7000 volts or even 11 kV. So in that case, each device should be rated for 11 kV, but we don't have, practically we have limitations. So how to overcome? How to make this 2-level inverter survive for high voltage and high power conditions? One is the problem is device rating. We have to overcome the device rating issue. So how to overcome? Instead of keeping one device, they keep a string of devices. This, I think this concept is already earlier known. This is nothing but string operation of the SCRs. When you have one SCR whose voltage or current rating is greater than that of, I mean, lesser than that of the required voltage, we'll connect string of SCRs in series or parallel configuration to meet the output voltage and output current requirement. The same concept was used where instead of one device, they used consequently multiple devices such that the overall, for example, the total DC link voltage is 1000 volts, let me assume. Okay, the device we have available is only 400, for example. So they will connect each device of 400, 400 and 400. So total string voltage will be turning, that means this switch voltage, the voltage across this complete switch is actually 1200 volts. So this is able to withstand the applied DC link voltage, and there will be a safety factor also, that I think you have you already know that from the SCR, conventional power electronics, you know those concepts. So yes, this is able to withstand the, that means the basic two level inverter is made to withstand the high power. That's okay. But the point, the again the disadvantage comes is when you already know, even though the ratings of the two devices are same in power electronics, because of the doping issues, right, we have the no VI characteristics of no two devices will remain the same. That means there will be a difference in the turn on and turn off times, right? This may lead to that of unequal voltage distribution, and they require externally the static voltage balancing and dynamic voltage balancing circuits to for this particular power converter. It is because no two devices, even though the rating is same, no two devices will not have the same characteristics. I think you can reliably take it from the SCR, where we will take one SCR like this and the second SCR like this, and we say that even though the rating is same, there will be a small difference in the BB naught and small difference in the leakage, which may lead to the unequal voltage distribution. So there we take again the static voltage equivalent component, dynamic equalizing component. The same problem holds good here too. So it cannot be useful. Other problem is that now we are increasing the number of devices, so gate circuits need to improve, increase the protection circuit need to improve. The overall cost turns very high, such that it may not be flexible to meet the high power applications. So they need a reduced, I mean a simplified configuration. It may involve multiple switches, but at the same time it should, these multiple switches should help in improving the performance. That means it should reduce the filtering size requirement, it should reduce the cost of the overall converter. So what they try to do is that they try to go for the other solutions, which is nothing but multi-pulse inverter. This is a common where two 6-pulse inverters are being connected with some phase difference between them. So this phase difference is created by using star delta and delta star transformers, that is called as zigzag transformers, and they are introduced. Again this turns to be complicated because because of the issue of cost and size and complexity. So what they try to go for the other solution, where now for in this we are using multiple switches in the high power two level inverter. So they try to do, instead of using the switches in such a way, let us connect the switches in such a way the appeared DC voltage can be added, whatever the DC voltage can be added. Okay, and they try to produce large output voltage. That means multi-level inverters uses the concept of addition of multiple small voltage levels and synthesize a large output voltage, AC voltage. Okay, so what is the advantage of this? That means it is as equivalent of using to multiple inverters and adding the voltage across the inverter. How they are not directly added, they are added with some delay between them, so that it produce a stepped output voltage. So this will make the moving average equal to sine, and this improves the harmonic performance and reduce the filtering requirements. Okay, so further how it is going to affect the device ratings, that we can see. This is going to affect the device ratings too. How can we ensure that? Right, for example, these are the popular multi-level inverters, but yeah, to make you understand how this is going to affect the DC voltage, let me tell you. For example, I want my output voltage of AC voltage of 200 volts RMS, whatever it is. Let me assume peak also. Okay, some 200 volts output voltage I got. So each voltage I have taken it as 100. So to meet the 200 volts, are we using 200 volt switching devices now? Is the voltage rating of the switch each switch 200? No, it is only 100 because when this switch is on, this switch should be off. Both the legs should be complementary. So each device is rated for VDC here. Each device is rated for VDC here. Okay, so the output voltage, that means we are able to use a mature medium voltage power electronic devices to obtain high power. You may think that it be 200 and 100, but in practical way we will be connecting multiple such multiple such H bridges, at least 70 to 80 depending upon the range, when we are whether we are going to which type of voltage range. For example, 11 kV if we go, we will connect at least 70 to 80. If we go 6 kV, so depending upon the voltage ranges, they will be at least 55 to 60 bridges which are being connected in cascade. So we'll try to add the complete voltage. But however, these switches are operated, these bridges are operated such that you get a stepped voltage. That means all the voltages are not given at a stretch. That means the switching pulses obtained for all the bridges was not same. It will vary. How this is going to vary? So for that, first we have to understand how this bridge is going to operate, how this each bridge is going to operate. The simple concept is there. I will tell you. For example, in this particular, take the same bridge. I think you know. Let us take the case of the VB1. VB1. You see this particular only this bridge, simple bridge. Now we were on S11 and S21. Whatever the voltage obtained is nothing but VDC. That otherwise you can take the example of this configuration where a simple converter with simple switches I'm trying to show. Okay, let it be S1, it is S2, this one be S3 and this one be S4. Now when S1 and S4 are on, if this is VDC, what will be the output voltage? Let this be VA and this point be VB. So VAB voltage will be equal to VDC when we on S1 and S4. Okay, similarly, when we on S3 and S2, VAB voltage will be equal to minus VDC. That you know very well. Okay, now when the voltage of VAB is equal to 0, when both the upper switches are on or when both the bottom switches are on, because there won't be any path. If, for example, if both the upper switches are on in this way, so that means it is removed. That means there is no written path. There is no written path. Only this path is there. There is no written path since both the bottom switches are off. So in this case, we will get 0 volt. In this case, you will get plus VDC. For example, if we turn on these two switches, okay, if we turn on these two switches, there will be a path like this where you can get minus VDC. That means every bridge has a potential of obtaining 3 levels. One is plus VDC, other one is 0, other one is minus VDC. So when we add two bridges together, what are the possibilities? This can produce VDC, bottom one can produce VDC. So with respect to this one, we can able to get, okay, with respect to this one, we'll get to it, right? 2 VDC, VDC, 0, minus VDC, minus 2 VDC. That's what? How? That means when both the bridges are on, that means this bridge is generating plus VDC, this bridge is also generating plus VDC. We can get plus 2 VDC. For example, if this bridge is generating minus VDC and this bridge is also generating minus VDC, you will get minus 2 VDC. In case if this bridge is generating VDC and this bridge is generating 0, you will get an output voltage of VDC. So such a combination we can make. Okay, there are multiple combinations that appearing in these cases. So these are called as redundancies. These are called as redundancies. This is the one of the advantage of this particular cascade hybrid multi-level inverter. Now let's see how this is being simulated, how we are going to get that particular voltage. So for that, I'll show you the simulation. Okay, for that I'll show you the simulation. I think the time may not be appropriate to see the reduced switch count also. So, is the screen visible? Is the screen visible where you can see the simulation, MLI simulation? Yeah?
I can see MLI simulation.
Okay, fine. See, this is a simple 3-level inverter. That's whatever I have said. So this is the same thing that was happening where I have operated with respect to 3-level. How to obtain this particular 3-level is able to see. We are able to make the simple H bridge operated for 3-level. So how to make this particular inverter operate for 3-level? It actually depends upon this one. This whatever the PWM that you are using. So there are multiple approaches for doing it. Okay, let me take this approach where you are using, it is like one sine wave compared with the triangular wave, you are getting one set of pulses. Second sine wave compared with again triangular wave, you are getting again set of pulses. We are using 180 degrees phase shift. That means our intention is to make sure that these two legs operated. That means when HA1 is on, HA2 is off. That means the first leg is going to generate VDC. Now, if I have to ensure the output voltage is VDC, in the bottom switch, HA3 should be on and HA4 is off. So, in such a cases, we have to make sure that there is a 180 degrees phase shift operation. That means in the upper switch of the first leg is on, then the bottom switch of the second leg should be on. So, there should be a complementary operation. So, for that, we take a sine wave as a reference for the first leg. We take the sine wave as a reference for the second leg, but both are at 180 degrees phase shift. So that's what is being shown here. And further, the comparison is being carried out with respect to the triangular, only one triangular wave, and you are able to get the pulses. When sine is greater than triangular, you are getting one pulse and complementary is given to the bottom. You have taken the second sine wave, which is giving 180 degrees phase shift. You can see it was pi shifted, and you are getting two more pulses. Again, they are given to the switches. That's how it is operated. Okay, so this is about 3 level, but going for 5 level, how it is going to done, right? In this case, the first leg has a potential of getting 3 levels and the second leg has a potential of getting 3 levels. That means how many, if it takes 0 as a common, so let's take 0 as the S side. So how many are there in capacity? So we have plus 2 VDC, plus VDC, 0, minus 2 VDC and minus VDC. So 5 levels are there. So one of the popular method for doing it is nothing but level shifted PWM technique, where we use multiple carrier waves. That means if we, now in this case, I want to generate 5 levels. So I will use 4 carrier waveforms and just try to distribute them evenly with respect to that of overall modulating signal, right? So in this case, if we try to compare whatever the comparison, we have taken 1, 2, 3, 4 carriers. If I take the first carrier C1, which is given with this particular magenta color, so when you compare with this particular carrier and the sign, whatever the output pulse that we are getting, that is responsible for getting an voltage band from V to 2V, because it is on the upper half of the sine wave. Okay, in case the carrier C2, which was compared with the sine here, that is responsible for getting a pulse from 0 to V. Similarly, if we take the next one, it is responsible for producing 0 to minus V, and the bottom carrier that is responsible for getting a voltage from minus V to minus 2V. So this is how is responsible for you know, that's it. The top, the first carrier is on the top. That means whatever the switching pulses are obtained, those are only responsible for getting an voltage magnitude of VDC to 2 VDC. If we expect the total output waveform magnitude should be 2 VDC. So the same thing, I will show it here. I think you can see, you can observe. See this one. You can see this one. In this case, you can see this is the PWM that we have seen. In this case, the top, whatever the pulses that are happening over here, that means 0.5 to 1, whatever the interaction happening with the carrier, whatever the pulses that are obtained, and they are responsible for getting an output voltage 100 to 200. Similarly, the pulses that are obtained from 0 to 0.5, they are responsible for getting an output voltage band of 0 to 100. So in this way, you can see, if you try to keep this particular on this way, making it in a normalized form, you can exactly estimate which carrier is actually responsible for obtaining a specific voltage band. Okay, so further, the key important observation with respect to this particular multi-level inverters is, for example, if I want to get the 2 VDC, that means the lower bridge should also responsible for obtaining VDC. The upper bridge is also responsible for obtaining VDC. That means, let us take this first waveform is the output voltage of the lower bridge. Second waveform is the output voltage of the upper bridge. So in this case, first when 0 to VDC is required in the output voltage, only lower bridge is producing the output voltage. In that case, the output voltage of the upper bridge is 0. When you want output voltage to vary with respect to 100 to 200. Then the upper bridge is, lower bridge is completely staying at 0, sorry, staying at 100, and the upper bridge is varying from 100 to 0 to 100, such that the output voltage again changes from 100 to 200. So what we try to do is that, what we try to observe is that the switches which are in this particular inverter configuration, these are the classical MLA configurations which are most popular. So what we try to say is that the switches which are responsible for getting the lower voltages, that means from 0 to VDC, they are still staying in conduction when we go for the higher levels of VDC to 2 VDC also. Right. So the same thing, I repeat the point. The switches which are responsible for obtaining 0 to VDC, they are still remaining high. That's still remaining high. That's still remaining in conduction when we want the voltage band of VDC to 2 VDC also. You can see, for example, let us take an instant where the carrier is between 0.5 to 1. The sign is between, the reference is between 0.5 to 1. In such cases, the pulse obtained with respect to the C2 is also high, because because sign is greater than that particular carrier too. So the logic, this particular PWM scheme is suitable only for the schemes where the lower switches remain in conduction at higher bands also. So that is the key problem. They have the overlapping issue. Okay, the pulses, the switching pulses produced by this particular PWM are overlapping. Is the slide changing? Can you see the slide? Can you still see the, can you see the slide? Hello? Hello?
Yes, we can see the slides.
Okay, fine. Yeah. So this is a basic problem with respect to this particular PWM. So what the, okay, fine. This is suitable for this. But when you go for the higher reduced switch count configuration, first, why would you have to go to reduced switch count configuration? Because of this, for example, in this case, M is the number of levels in output voltage, and these are the switches required in per phase. We talk about cascade H bridge. Now 5 level. In case of 5 level, how many switches are being used? How many switches are being used for case of 5 level? 8 switches are used in each leg. 8 switches are used in each leg. But in case if we want to go for the next level, where I want to get an output from plus 3 VDC to minus 3 VDC. So I have to use 3 bridges, where there will be 12 switches in each leg. So overall 36 switches. Okay, now when you go for next level, again it increases. The number of switches keeps increasing. Okay, the number of switches keep increasing. So this completely increases the driver requirement, protection circuit requirement, heat sinks, all the control. This overall making the complete circuit bulky. So what they went for the reduced switch count configurations. So the key main agent, there are multiple reasons for developing this reduced switch count configurations. Okay, but since we are going on the baseline, let's see how would be the reduced switch count configuration work. Okay, so this reduced switch count configurations involves the reduction in the switch count compared to the conventional classical MLA configurations. Okay, so since we have seen 5 level, I'll show 5 level only. So these are various configurations which will be used. There are different categories in this, how we are going to use H bridge and remaining switches. So these are called a separate polarity generator, where the right side is responsible for only generating the levels, and the left side is responsible for generating the voltage polarity. So they are polarity generators. So there are multiple types in this, how we are going to use the H bridge and all. But since we are focusing majorly on simulating and how to make the PWM applicable for RSC MLI, let me take one of the simplest configuration as an example. Okay, you can see the slide of T type, right? So this T type is one of the simplified configuration. This is also responsible for 5 level. This overall 3-phase structure, let us see only one phase. That means in each phase they are using how many switches? 1, 2, 3, 4, 5, 6 switches are there. 6 switches are there. Okay, so how many levels it can produce? According to this condition, if I turn on S1 and S4, if I turn on S1 and S4,
5 level is 511
yes?
slide is there, ma'am. 511 simulation results.
Yeah, I think the slide.
Okay, I think the slide was not changing again. I'll just reshare it again.
Oh yeah.
Is that visible?
Now is it's okay, ma'am.
Yes, it
Okay,
is okay.
T-type topology. So in this case, if you see, if we turn on S1 and S4 switches, if we turn on S1 and S4 switches, right, the voltage between VA, let me call this point as some other terminal, okay, this voltage between VA and other end of the terminal, N, let me call that point as N, okay. So this voltage VAN is equal to 2 VDC, right, if we turn on S1 and S4. Similarly, if we turn on S4 and S5, if I turn on S4 and S5, the output voltage VAN is equal to VDC. Similarly, if I turn on S2 and S3, okay, the voltage across them is equal to minus 2 VDC. Okay, why minus 2 VDC? Because this plus is coming to the N terminal and minus is coming to the A terminal. So again, VAN voltage will turn to minus 2 VDC. Similarly, if I turn on S6 and S2, the voltage will be minus VDC. So in this configuration, the first point observed is, for example, S5 is responsible for obtaining VDC. S5 is responsible for obtaining VDC. That means S4 and S5 are on. Okay, that's okay, fine. Right? But when you go for 2 VDC, the path is S4 and S1. That means the switch that is responsible for obtaining VDC is not in condition for obtaining 2 VDC. Whatever observation that we drawn from Cascade Hedge Bridge, a popular PWM technique, that is level shifted, is not applicable here. So we need some other techniques where the switching operation can be changed as per the desired condition, as per the desired operation of the inverter. So like this, there are enormous configurations where the switching operation keeps changing. There is a path, but as per the path, you have to give switching pulses. Then only you can get the desired output voltage. So how does that happen? So for that, there are various methods are involved. The key objective of this particular method is to make the overlapped pattern as a non-overlapped pattern. That means you can see the level pulses. For example, if P1 dash, P1 is the pulse responsible for obtaining 0 to VDC. Is the slide changed? Is the
Yes.
slide changed?
Yeah, yeah.
Okay,
Objective
yeah.
PWM schemes of RSC MLI. Is
You
that the
can see
slide?
objective PWM schemes of RSCMLA. That's what you can see, right?
Yeah.
Yes,
Okay,
ma'am. Yes.
yeah. In this case, P1 is responsible for obtaining 0 to VDC. P2 is responsible for obtaining VDC to 2 VDC. P3 is responsible for obtaining VDC to, sorry, 2 VDC to 3 VDC. You may wonder how I am telling. It's just like a moving average sign. See, if I try to draw a moving average sign, how I will draw? Obviously, if I try to draw moving average sign, I can't make like this. I can make only moving average sign like this. Yes, here it is less, here is little more magnitude, here is large magnitude. This is how I am trying to say. It is VDC, let me call this is VDC, and this point is 2 VDC. Let me call this point is 3 VDC. So this pulse P3 is responsible for obtaining an voltage band of 2 VDC to 3 VDC. Whatever this pulse P2 is responsible for obtaining voltage band of VDC to 2 VDC. Similarly, the lower pulse P1 is responsible for obtaining voltage band of 0 to VDC. This is how actually pulses are obtained. But what the point, the same focus, we have an overlapped pattern. The pulse responding for lower voltage levels is remaining high even in higher levels. That means P1 is high for even P2 high and P3 high. P2 is high when P3 is high. Okay, so we have such kind of issues. So we cannot apply for the other topologies. So what they try to do, only the pulse should remain active only when it's interacting with the sign. So when we try to compare now, only with respect to those interaction, the pulse should remain high. Remaining time, it should remain active low. So it should only remain only when the sign is interacting with the carrier, then it should remain low. Only when sign is interacting with the carrier, it should remain high. Only when the sign is interacting, at that time only it should remain high. Remaining times it should remain low. So these are non-overlap desired pulses which can obtain the required pattern. So how to obtain this conventional pattern to non-conventional non-overlap desired pattern? So for that, there are different methods that are used. Okay, multi-reference PWM, reduced carrier PWM, switching function PWM, where they will use less than and greater than combinations, and you can get it. Okay, not only this, there are other multiple logical methods are there. But whenever we study a method, we have to ensure that that particular method is suitable for multiple configuration, so we can analyze it easily. So okay, that comes. So for that, let me take an example of reduced carrier PWM technique. You can see reduced carrier PWM now. Since previously also we have seen this kind of arrangement, it will be very easier to understand. Let me pick up this particular, the lower method, and just tell you how this is going to happen. Okay, so my intention is to make that this reduced carrier PWM, whatever the pulses that are obtained, make sure you try to do something with the pulses such that this is suitable for the desired operation of the, for example, considered 5-level T-type configuration. So the same thing, the reduced carrier, what we are trying to do is that, why you are taking reduced carrier? Because you can see the carriers are not placed in the bottom, the carriers are only placed in the top. But if you take only in the top and we don't take in the bottom, that means the bottom also should take as a mirror image of the top. That means completely sine, it is converted to the absolute value of the sine. It is compared with the two carriers and we are getting two pulses. This pulse is P2, this pulse is P1, because this is responsible for obtaining voltage band of 0 to VDC. This is obtaining an voltage band of VDC to 2 VDC. Again, you may wonder why I am telling it. Just to keep both of them over here. This will come over here and this will come here if you try to keep. Because this value is, if you try to keep it again, it happens in the same way. If you try to keep on together, it turns to be the moving average. Okay, right. You can see this comparison here, it is having large. So that's why you are getting this pulse is actually obtained by comparing this one. Whatever this pulse is obtained by comparing this carrier with this sign. So this is the first stage where you are generating the carriers and comparing the carriers with the sign, and you are generating these two pulses. These are also overlapped, where the lower pulse, which is responsible for obtaining voltage band of 0 to V, is still remaining high when the voltage band of V to 2V. So these are not directly applicable to the considered topology. We should do something with this. So there comes the second stage where we will try to make this particular levels as the independent. You can see this V is not remaining high at the upper levels. Here it is remaining high, but it is like when this is low, this is remaining high. I'll tell you why this is happening. Okay, because now we have the voltage band 0 to V. Okay, we have the voltage band V to 2V. We have an voltage band 0 to V, V to 2V. Okay, that means how many levels are there according to this? According to the topology, you need one path for getting 0 voltage. You have another path for getting V voltage. You have another path for getting 2V voltage levels. So for that, this is obtained with respect to P1, this is obtained with respect to P2. That means when P1 is high, we get voltage level. When P1 is low, we are at 0. Similarly, when P2 is high, we will get voltage level 2V. Together, we are getting this one. That means when that's the reason why we got this is responsible for 0 voltage, this is responsible for V1, this is responsible for V2. That means this is remaining high when the 0 is low, and this is remaining low when V2 is high. So that's the combination we are trying to obtain, and we just keep that in a MATLAB functional block and try to obtain. Now after getting these pulses, whatever the pulses that are responsible, they are not responsible for bands, they are responsible for the specific voltage levels. So for every level, that means for a positive voltage level, I got one pulse 2V. For positive V, that means this is responsible for plus 2V. This is responsible plus V. This is responsible 0 in positive half. This is 0 in negative half. This is responsible for minus V. This is responsible for minus 2V. This is how we got the pulses. Now these pulses need to be directed to the converter. Stage 3. So until here, this is common for any configuration which is 5 level. It can be MLDCL configuration, it can be cascade H bridge, it can be reduced switch count, any configuration. This particular stage, that is stage 1, stage 2 is common. The difference lies in stage 3, where you have to direct these pulses as per the switching operation of the inverter. Okay, so that's how you can see this is common. I have taken two inverters, simulated both of them to obtain the desired output voltage. I have taken the same thing. The combination is changed in this. Now, how it is changed, I will show you the simulation. Okay. I will show you the simulation now. Okay. Is the screen visible where you can see the MATLAB?
Yes.
Yes, ma'am.
Yeah, okay. See this one. The first one is the T-type topology. Then second one is some other configuration which is called as MLDCL configuration that I have taken. My aim is I have used a PWM and made it as a universal PWM. That means it is able to applicable for both topology 1 and topology 2. So for that, what they try to do, yes, we have stage 1, we have stage 2, yes, we have stage 3. So how it is going to happen with respect to that? This MATLAB function block, yes, this I have done some modification where I can obtain an independent pulses, where pulse P2 is responsible for obtaining P2, but V1 should be high when P1 is high and P2 is low. That's how, that means you can see V1 is obtained with respect to the P1 and with respect to the P2. How? That means V should be obtained in 0 to V band and V to 2V band also we have V. That means V should be obtained when P1 is high and P2 is low. So that's how it is, simple logic, just a common logic, simple logic which can be delivered with the simple common sense and all. Okay, further what we try to do, we have to direct these pulses as per the desired operation of the inverter. So for that, what we take according to this particular configuration, okay, according to the configuration, is a slide changing? Is a slide changing, ma?
Yes, yes.
Yes, you can see the circuit where in this S1 and S4 are on, you will get VDC. So that means S4 switch is responsible, S1 switch is responsible for obtaining 2 VDC. The same thing we have done. Okay, S1 switch is responsible for obtaining 2 VDC. S3 switch is responsible for minus 2 VDC. You may wonder why we have taken 0 and N also. So it is also for 0. I told you now for 0 path, yes, top 2 switches can be on or the bottom 2 switches can be on. Similarly, S5 is responsible for obtaining positive level in the V1. Similarly, S6 is responsible for obtaining minus V1. Okay, that's how we have directed it. Okay, and then the same thing is done. Okay, where you can see that whatever you can see the 5 level output voltage. Can you
Yes.
see the 5 level output voltage? You can see 0 to VDC, VDC to 2 VDC. As just this is changed as per the desired operation of the inverter. Okay, just as per the desired operation of the inverter, we are going to change it so that we'll get the pulses. You can see the PWM, everything is being same. This you can see this PWM, how this PWM is. See the same thing. It is reduced count where you are using 2 carriers. So these carriers are actually taken depending upon the voltage magnitudes that are being required. Okay, now in this case, the voltage magnitudes are V and 2V. I'm not bothered about polarity because I'm just using the same pulses in the second end also. So 2 magnitudes are required. So for that, I have using 2 carriers. If 3 magnitudes are required, V, 2V and 3V. In that case, I'll use 3 carriers. So these carriers are actually N minus 1 by 2. Okay, for 5 level, we use 5 minus 1 by 2. 2 carriers we use. Okay, so the same thing is given for other configuration also. In this configuration, it is like 2 chopper cells which are connected with the polarity generator. Each chopper cell can generate an output voltage of VDC. That means this can produce VDC and 0, and the top one can also produce VDC and 0. Both together, they can produce an voltage of 2 VDC to. This is how you can see. Same PWM I have given. Both MLDCL, multi-level DC link inverter, which is a second configuration, and T-type, that is a first configuration. Both are able to generate a 5-level output spectrum. So where is the basic difference that is emerging? It is not in the stage 1 or stage 2. It is also in the stage 3, where we are going to change the code as per the switching operation of the inverter and make it universal. Right? So this method, here also you can see the overlappedness. Here the overlappedness can be seen over here. Okay, but when you go for the next, where you are getting here the first stage, whatever the pulses we are getting is as per the bands. They are as per the bands. Here as per the levels. Okay, and the third stage output, whatever we are getting, these are getting as per the switches. Okay, so this is how we operate it. Okay, we can use the same method for any configuration, but it remains same as per the levels is same. The levels are changing. We have to increase the number of carriers and then we have to change the operation as per the desired inverter configuration. Okay, this is the same thing here we have done. Here I have used the cascade hedge bridge. This is the output voltage of a cascade hedge bridge. You can see 5 level, and both the CSB lower and CSB output 3 level output waveforms are also shown here. Okay, I can even show you the 3 level output waveform of this This one is single hedge bridge. Only one hedge bridge is there, where output is varying from plus VDC to 0 to minus VDC. This is unipolar PWM, where the output is varying between VDC and 0 at a time. Okay, and this one is a 2 level inverter. As I told, I'll show you later. This is how we simulate it. Okay, you can see how the output is changing. The first one shows the line voltage of all the phases, VAB, VBC and VCA. But next three is nothing but VAB is shown in one plot, VBC and VCA. You can see a phase difference between them. So this is how the phase difference is being seen. Got it?
Yes.
Okay, right. Yes. Okay, this is from my side. Any doubts?
Yeah, so is the presentation over, ma'am?
Yeah, it's over.
Okay, great. So
Okay.
that was
Actually, I'm just checking out the time. It is 1 hour only, na?
yeah.
So still we have time. 5 minutes, I think.
We have 5 minutes. Maybe we can take questions if
Yes, that's why. Okay.
Yeah. So anybody, the floor is open for questions. Thank you for that wonderful and very quick and very clear presentation. Any questions from the audience? Maybe I can ask couple
Yes. Yeah.
of questions. So as you said that we go for more number of switches because a particular switch cannot take the entire VDC if you're going for a
Okay.
high
Yes.
power
Yes. It is about the device rating limitations.
device rating limitations. So
Mm.
what at present, what is the state of the art as far as a single
4.2
device?
kV. With respect to the IGBT, if we take, the
Yeah.
voltage rating is 4.2 kV.
So
But the point with respect to this one is, for example, I can tell you, when you got a new equipment, a new sophisticated equipment, the cost will be little higher.
right.
Okay, so when we want to make it most effective, we have to use a range where it turns to be a mass protection, and it is turns to be more easier,
Right.
and it is directly into the market, open in the market. So in such cases, we used only matured medium power electronic devices. So what does matured medium means? The technology is so matured such that the cost is acting so much less.
Right.
So we have to use medium power electronic devices. Yes.
Okay. So what would be the cost of, I mean, you're saying 4.2 is the absolute tops, but
Okay.
if when you're
No,
talking
it's like even still it is increasing 4.2 kV depending upon the frequency, current, and voltage. But as per this, yes, 4.2 is there till now.
4.2 is there. And the second question probably that I would have is like you have talked here about 5 levels and inverters, and I mean I am not a power electronic person, but I have
Okay.
seen a lot of students
Okay.
present. So they go on to 7 levels, 10 levels, and all that. Now the big question is,
How many levels we can go? That's where would be the optimum level. That's what, right?
my question is yes, at much higher levels, is there any benefit or like already? I mean,
I
how
can, yeah,
beneficial
that's
is it?
actually, it's
We'll
about
see.
the harmonic spectrum. Actually,
Yeah, TST.
actually about the harmonic spectrum. But actually, if I try to take, see, for going for higher levels, if harmonic spectrum is the only reason, there is no need of going for multi-level inverters. You can use a filter. Use a
Right.
simple
Exactly.
filter, make the PWM increase, because when you go for the PWM, basic even 2-level inverter also, what that happens is that I'll show you one slide. For example, in this case, you see, in this case, right, is a screen visible where you are showing high power 2-level inverter. It's a simple
Yeah.
2-level inverter only. You can
Right.
see the harmonic, maximum harmonic at harmonic order 20. Harmonic order 20 means 20 into 50. It is 1,000 hertz. That means the switching frequency is 1,000. That's the reason you are getting maximum harmonic there. And remaining are all the lower order harmonics. That
Correct.
means in this case also, if I increase the switching frequency, I can push this harmonic still higher.
Right.
There is no issue. That means if we go for the higher switching frequency, obviously the filter size reduces. So if I really want to improve the harmonic spectrum, and for that only I want to go for the multi-level inverters, no, absolutely no. You can quickly use a filter and increase that particular switching frequency and make it suitable. If the
Right.
still it is not suitable, 5 level will be sufficient. That's why most of the drives, to
Right.
reduce the torque ripples, they will stick for only 5 level. They won't go for 15 level, 35 level, or 37 level, somewhere like that.
Correct.
Okay,
Huh.
these levels are suitable only when you go for the medium ranges where the DC link voltage is 11 kV, 66 kV, or some which is very high, such that each
Okay.
module cannot operate. And in case if one module fails also, you should have a backup of other module, which is called as
Right.
reserved modules.
That
So
makes
there
sense.
are that's why we go for the levels. And however, in case of the academic standards, when we
Yeah.
want to go for the research standard or practical application, they have to start at some or the other point. So that's why they will try to apply the number of levels. But as because I have been working on the multi-level inverters from past 6 years, and from my knowledge, if you strictly ask me why we have to go for number of levels, it's only depending upon the desired rating. That's how it designed. They will take the overall output requirement with respect to the DC requirement, with respect to the switch voltage requirement. For that, what is the available voltage requirement, then available device requirement, then they will take multiple modules and they will do it.
Okay. That's great.
Yes.
Great to know. Thank you so much,
Thank you.
Dr.
Okay.
Haripri.
Right.
Yeah.
Yes.
Uh,
Right. I would
anyone
like to.
else has a
Yes.
question? Yeah, please, please go ahead.
See, I'm very happy to share my experience or knowledge over with you. But what I feel is like, try to make the sessions interactive. It may not be this way. I really appreciate the way the sessions are being conducted, the initiatives are being taken out to exchange the knowledge between the research and the UG students or PG students background. But if it is not going to go the end user, or if it is not going to benefit the students up to the maximum extent, or else to the optimum extent, all your efforts are going to be in vain. It's not going to be that much. So always the session need to be interactive. If try to make I know how much probability it is there from your end, but it's only from it's from my request that if
Definitely.
even if the session is being 10 minutes or 15 minutes or 20 minutes or whatever it is, the topic need to be interesting and they need to be attractive. And second thing, organize a series of lectures such that they will come, they make it more interactive, make it more hands-on. Maybe if after the COVID you may try
Yeah,
that.
I think I'm sure we can definitely invite you here and we can have a workshop, a physical
uh,
workshop where you can interact with the students and, demonstrate this and maybe they can also try their hands at the.
Actually, always the students will be interested on their end if they see it on a practical application. Otherwise it
Exactly,
won't be
absolutely, totally agree with you.
such conditions. We can make a small demo versions and demonstrative conditions on the MATLAB and make the students to develop their own modules and try to apply the for mathworks and all such kind of things you can try. But always make the session interactive. If the session is not interactive, how far you are going to keep the effort, these are not going to be useful.
Absolutely.
Okay, right.
Yeah.
Thank you for the
Thank you so
initiative and
much.
thank you for calling. Right, thank you. Fine. Shall we end the session? Yeah,
Yes, if
yeah,
anybody
thank
else has any questions, otherwise we can end the session.
No, no, I think hardly we can expect. Thank you. Bye.